This section is mainly about the properties of these guys, but just to reiterate some stuff, we've talked about a lot of properties already. So anything we've talked about with like ionic and covalent and the properties of those guys and like the different states that they are, make sure to remember those too. And again, the focus is on why, so make sure you know why those properties exist. But we'll talk about some other ones in this section. So there's stuff you can watch in the College Board video that's on the website. So I recommend watching that. There's some stuff that I'm going to go over here that isn't on that video. So there's fluidity, which again I'll talk about in a second. For now, just know it's flowing past each other for vocab term purposes. We have compressibility, which is, as you assume, compressing something. And so you're changing that volume when you're applying pressure. P is used a lot for, a shorthand for pressure, so just be aware of that. And so this is pretty common sense stuff because this is stuff you can see in your life. When you have something that's solid, you can try to compress it, but it would be very difficult. It still stays as a solid for the most part. So that's why it says nearly not. Same with a liquid. You have a liquid water, you try to put pressure on it, it's not gonna really compress. It's gonna remain water, again, for the most part. But a gas is very compressible. If I have a gas in a container, like think of just a random container, and I put pressure on the lid of the container, if no gas escapes, you can still press the gas, with some capabilities, with just your hands or a machine or whatever, depending on what you are doing. Liquids have some properties that you need to know besides the ones we've already talked about. So an example of this is surface tension. Before I even touch surface tension, remember in Unit 0 we learned about density, or relearned from previous classes and such, that if you have water has a certain density. If I put an object in the water and it sinks, that means that object has a higher density compared to water. If that object had a lower density, it would float on water. However, there are things that are denser than water that can still float in water, and that's because of surface tension. So surface tension is defined here, where you're just trying to find the minimum area that a surface can do its thing, and I'll talk about what that thing is in a second. So it's trying to resist the external force of the object that is on that water. And if you're like, huh? So think of like a random object you're throwing in water and it somehow floats. So for example, you have this sphere here. Let's say it was like a fat metal that is super dense. And despite it being super dense, it still floats in the water. And so the reason behind that is, again, surface tension. So the water molecules have IMFs. They're attracted to each other via hydrogen bonds, specifically as the IMF. And so because of those interactions, those IMFs, that ball will rest on top of that water despite being denser. If it gets pushed a little bit more into the surface, it would probably sink. But if it was placed gently in the water, for example, there might be enough surface tension from the water to be able to hold it up. So that's why these bugs right here, this is called a pond skater. And so these are heavier than water in terms of density, and they can, do this floating water action thing because of surface tension. You have, again, the water molecules are attracted to each other, and so the legs of the pond skater are not putting enough pressure to break those hydrogen bonds in the water. And you can see in the picture here, the legs are slightly indenting the water. You can also see it in the cartoon version. And so the leg slightly indents that water, again, similar to this picture over here. And that's actually increasing the surface area that the surface tension can be at enough. If there was too much pressure, then that bug probably would sink. Another thing that isn't related to surface tension, but in case you just wanted to know, is that the legs of this bug is hairy, and the hair on their legs is actually a non-polar bunch of molecules. I don't know which ones off the top of my head, but because they're non-polar, they're hydrophobic, and so there's not really much IMF action happening between the hydrophobic molecules of the leg hairs and the water. So that's another reason why they're not going to sink to the bottom as they do, or, other things. The other property to know is capillary action. And so you can see this tube here. If you insert it into a liquid, you'll see that, meniscus, as you've seen with like graduated cylinders and stuff, if it's small enough. And so there are adhesion forces and cohesive forces. So adhesion is the IMFs of the liquid that you're studying. In this case, this is water example, and the container itself. So there are IMFs that are happening here between the water and the container, like this, probably like a tube straw or something, right? And so there's interactions happening there. And then there's also the cohesive forces, which are the IMFs between the particles of the liquid. So in this case, it would be water molecules. And so in the capillary action where this is happening, the adhesion forces, the adhesion IMFs, are greater than the IMFs of the water, hence why it will interact in this way and go up. If they were about the same, it would just be leveled off, like just straight across. But because there's some attraction between the surface of that container and the water is why it goes up. So an example of this is water in a straw. So if you look at a straw, you put it in water. If you look very carefully, you'll see a tiny little meniscus, and you'll see that. So you have, again, the surface of that straw to that water. It is a bigger IMF in terms of strength compared to the cohesive IMFs of the water molecules to each other. So that would be an example of that. Another example is plants. So plants will, take in water because they need to, obviously, to grow and such. And so the plants have on their surfaces IMFs that are making the water move. There's other stuff that you can learn in a biology class in your future if you decide to go that path. But for now, we'll just talk about like the little chem side about it. So again, the plant itself, like the roots and the stalk and whatever else, depending on what plant you're talking about, they have the IMFs that are interacting between the water and whatever that water is going through in order to travel to where it needs in that plant. So that is another example of capillary action. The last liquid property you really need to know is viscosity. And so if you don't know what viscosity is, the definition is just resisting to flow, specifically for liquids. And so if you have something that has really strong IMFs, then you have a higher viscosity. If you have a higher viscosity, aka it will not really flow very well, then that means you have a thicker liquid. You've seen this with an example of maple syrup, like this guy right here. If I pour maple syrup in a different container, like or even pancakes or something, you notice how it doesn't flow very well, and that's precisely because the maple syrup molecules have pretty strong IMFs, and so they don't want to flow very well, so that's why you have that thick syrup. So again, we've talked about density before, but some other stuff to mention. Now, it's kind of obvious, but in case you need to know, solids are usually denser than liquids, and then, again, solids are usually denser than gas. That's not always the case, but it is most of the time. And so, as I said right here, not always. So an example of this is water. So think of, you have a drink in your hand, some kind of drink, who cares, and then you add some ice in it. Well, the ice is floating, but ice is a solid. So why the heck is it floating even though most solids are usually denser? And so ice is less dense than water as a liquid because of the structure it has. So you can see here is ice. And so the IMFs, the hydrogen bonds that are holding the water molecules, you can see the interactions here, kind of. I mean, this is the best you can with a flat image of some 3D molecules, but whatever. So they make this kind of, patterning as you see here. And you notice that there's no molecules in the middle of these hexagons. And so because there is nothing here, there's space. And so since there's space, it's less dense compared to liquid water. If you have liquid water, these molecules are not arranged in this nice pattern that's forcing the hydrogen bonds to be like this. And so water, as you would have here, it's kind of swishing around. And so that's why ice floats. It's because it's less dense than water because the IMFs, the hydrogen bonds. And so same goes for any kind of icebergs you've seen or anything else that is, floating in terms of ice versus water or whatever liquid that ice happens to be on. There's, again, as a reminder, the formula you need to know. So again, it's on your constant equation sheet, but most of you probably memorized it already, so just make sure you remember it. Or, look it up. Gases have a specific property that you need to know about in a very, very specific situation. So there's something called vapor pressure, and it is this dynamic thing that happens, okay? So imagine you have a closed container like the one in the middle here, and when you have a closed container with a liquid, it can evaporate to a gas, and it does. So let's say the container didn't have any gases originally, it was closed off. When it's closed off, some of that liquid will become a gas, and that's that, okay? And so there is a certain amount of gas molecules that can exist in that container, some threshold. When that threshold is reached, you are at equilibrium. You need to know what equilibrium is. We will talk about equilibrium in way more detail in a future unit. For now, you need to know that the rate at which the liquid is changing to gas and the rate at which the gas is changing back to a liquid are the same. So even though the threshold has been reached to the gases forming in this situation, they're still going to continually change from liquid to gas and gas to liquid. But the amount of gas particles that exist stays constant. And if you're like, huh? Then I will show an example with an animation on the next slide. Again, we'll talk about equilibrium way more in a future unit, but you do need to know for the context of vapor pressure what that is. So that is the situation that's happening here. Again, you have a liquid evaporating into a gas, and the gas particles are also technically going back and condensing into the liquid. And so when you have that gas in a container like this, the gas puts pressure on the walls of that container. And so because that gas is putting pressure on the walls of that container, that is what is known as vapor pressure. Vapor pressure can also happen in the situation where a solid goes directly to a gas. So it skips the going from solid to liquid phase, and so it's just going from solid to gas. That would be sublimation rather than evaporation. So just make sure to know that you have evaporation here, but you can also sublimate from solid to gas, and then you can go back gas to solid. Okay. And so again, we have the gas pressurized. It is pushing onto that wall. So make sure to know that. Okay. And so you need to know why, when you're increasing temperature, the pressure of that vapor is going to increase. So I want you to think about it first before I yap about it. So see if you can figure out why. Think about molecules moving, okay? All right, ready? So when you increase the temperature of particles, those particles are going to move around a lot more. They have more kinetic energy, so they're going to move around more. Because they're going to move around more, they're going to bounce off the container's walls more. And so you can feel the pressure of those gases on that container. And so since they're moving more, they're going to bounce more and thus more pressure. So that's why. Now, the other thing you need to know is about IMFs of the liquid specifically. So if that liquid in this situation has a high IMF, we have a weaker vapor pressure. So see if you can figure it out first, and then I'll talk about it in a second. Okay, ready? So if the liquid has high IMFs, the IMFs are really strong in that liquid, that means that the attractions of the liquid particles are big. If they're big, that means they don't want to be a gas as much, and so you'll have less gas particles. When you have less gas particles, that means that you'll have less pressure because you have less particles bouncing off the walls or wherever it's bouncing off of, and so that's why you have less pressure. So make sure you know what vapor pressure is, what situations they can come from, and then what happens when you're increasing or decreasing in temperature, what happens with higher IMF liquids versus lower IMF liquids. Okay, what is equilibrium? If you're like, huh, based off my explanation. So here is a quick little 10-second video. You can see the particles are moving around. So you can see here, some of the particles are, let's play it again. Some of the particles are evaporating, but then you notice that one that bounced really fast. Some of them are becoming liquid again. And so this is a dynamic process where some of them will continually become a gas and some of them will continually be a liquid. But at equilibrium, the amount of particles that exist as a gas and the liquid will be constant. So even though they are constantly changing between the phases, the amount that exists are going to be the same at equilibrium. So that's what it means. If you are still confused, there is a YouTube video I will link on the slides. I'll even link it literally right here. And then I'll also put it on the class website, and I'll also put it in the description. Now, this YouTube video is talking about from solid to liquid and liquid to solid, but for the purposes of learning what equilibrium is, it's one of the best short videos that explains equilibrium in the context of what we need for this particular section. Okay, so I went over some properties that weren't on the College Board video. However, I think the College Board video is great, so I didn't want to re-lecture on stuff that they covered. So you need to actually watch the College Board video that relates to section 3.3. So make sure that you do that, because I'm not going to talk about it in this video. I only talked about the stuff that wasn't on there, but you do need to know the stuff on that video as well as this one. Okay? Okay. So here is your turn for stuff related to this section. So here is a multiple choice question, and here is an FRQ where it is only one part of it. There's other parts related to it, so you can see behind right here. Make sure to pause the video and try it yourself before you check your answers. All right, ready? Here we go. So for the MCQ, answer is B. So they're easily compressed because remember that the particles of a gas are very far apart. Since they're very far apart, you can put pressure on that gas if it's in a container of some kind. And so when you put pressure on that gas, those particles can get closer together, but not enough to become a liquid until you put so much pressure that you can actually condense it if you need to with enough pressure. There's plenty of machines that can actually do that. We don't have that capability in our classroom, but it is possible. Okay, FRQ. So this is an FRQ that might be confusing as I said in the slide, doing the guess method helps to organize your thoughts and drawing helps a lot. And so you're given this container, this flask. It has some air in it. It's sealed, so it's just some good old air with 644 mils, right? And so the density of the air was given at STP, so standard temperature and pressure, and so that's what's given here. The flask with air, again, right here in grams, if you have an unknown gas that was changing the air that was in that flask to now some unknown gas, now you know that, right? And so what is the mass of this unknown? So we can do some quick math. So we have our density formula, and so in that density formula, you can rearrange it to get the mass. I can plug in the values for density and volume that was given. Volume specifically of the air, because we know the density of the air, and we know the sealed flask volume of the air. So it's not the one with the unknown. I do that math, and so you can see right here, it's 0.831 grams of air. So you do that math, right? And then you can take the mass of the flask by itself, because now I have the mass of the air we just calculated. I could just get the flask by doing, the mass that was the flask with the air, subtract the air in it, and then you get that mass. And so here's the math for that real quick, and then there's our math. And then mass of the unknown, well, I now know the flask's mass, and now I could just get the unknown's gas by subtracting that. And so I do that subtraction, and then I get the mass of the unknown gas. Whew. Now, like I said, drawing a picture of this would have helped a lot. Like if you drew a picture of a flask and you labeled it has air and it has a 644 mils in it, and then it's the mass of that container is 121.03, and then you drew the other things, it would make sense. So if you're like confused about this math after I went over it, I highly recommend drawing what's happening in this situation to understand it fully. Perfect. So this is a diagram I've shown before, but make sure you know it. So make sure you know the solid, liquids, and gas properties and why they exist. You can talk about IMFs now more, you could talk about other stuff, so just make sure you got the solid, liquid, and the gas as you see right here. So as we've mentioned before, solids vibrate in place, so you can see the little vibration GIF right above. And so if we were able to reach absolute zero, which is 0 Kelvin on the temperature scale for Kelvin, they wouldn't be moving at all. We as a science community have not reached the absolute value. We've gone pretty close. I don't remember how many decimal points off, but it's like 0.0001 or something Kelvin. So we've gotten close, but not absolute zero. So the hypothetical of an absolute zero is they would not move at all. So particles, they again move around, they're vibrating, but they're not going around each other because they're kind of semi-locked in place besides the vibration. And so as a reminder, in a solid, they are not always close together. A lot of the time they are, but not always, like the example I talked about with ice versus liquid water. Okay, liquid, we have the mutual forces sliding past each other. So, we see the flow of the liquids right behind, right here. And so you can see that they're flowing around each other. They can bump into each other, that kind of thing. And so they're moving fairly fast. And because they're moving fairly fast, they do have, some IMF attraction, a little bit, but because they move so fast, they're not locked into place. And so those IMFs are, forming and breaking constantly. So those interactions are, fairly frequent in a liquid. They're still able to slide off each other as well. And then gases, so, if you need to know clouds, for example, clouds you think of as a gas, but there's technically liquid and solid in there as well. And so there are attractions to gas particles to each other, but usually they're insignificant. So, these gases right here, they're moving around, but as they get close to each other, like as they slide past each other very quickly, there is a tiny IMF that could form, but they have so much kinetic energy, they're moving around so much that IMF is forming and breaking so fast. And so, again, as a reminder, pressure is just the particles bumping into whatever container is measuring that pressure. If it's above boiling point, again, those attractions, those IMFs are not significant. And so they move randomly. Okay, they move randomly in straight lines. If they collide with each other, then they're going to bounce off each other, but again, in a straight line, that kind of thing. And then the space in between the particles, between liquid versus solid, well, gases are significantly more spacious. Here is a your turn. And so it's a very nice and easy your turn. So it's an old FRQ from the old standards, but it still works for a good example just to do real quick. So go ahead and do this, pause the video, and then check your answers in a few moments. Ready for the answer? Here we go. So there are 3 criteria you need to follow. So the first one is the fact that, matter cannot be created nor destroyed. So it started off with 6, you better have ended with 6. If you did more or less than 6, that would not have gained the point for this problem. The other things, as you can see right here, is molecules remain together as only intermolecular forces. So they have the atoms that are bonded to the center, so the nitrogen and the hydrogens, but there is no real interactions between one ammonia molecule versus another ammonia molecule because of the third bullet point, that there is a lot of space between the molecules. So, this is a nice, easy FRQ. You hope to have something like this on the AP test, so just be aware that you do have to make sure you count how many things you're drawing. And that is the end of this section. Make sure you know the properties, make sure you know why they exist, especially in the context of IMFs. Make sure you know all the properties that we've learned before, and like I said earlier, watch the College Board video on this section because there are other properties I did not go over. Alrighty, see you next time. Bye!